So we'll continue our discussion of Huffman's algorithm, and we'll prove that the Huffman algorithm gives us the optimal prefix code with minimum possible average bit length. So first we write the iterative algorithm and we'll prove its optimality by induction. So we have iterative algorithm. Iterative algorithm for Huffman encoding. So same idea we apply. Suppose the input is set S and the alphabets are A1 up to AN. And with the corresponding frequencies FA1 up to FAN. So we maintain a min-heap. Maintain a min-heap. Using the frequencies. So again, for simplicity, we can assume that the alphabets A1 up to AN are such that they are sorted in decreasing order. So just for simplicity, in explaining the algorithm, assume that FA1 is greater than or equal to FA2 and so on up to FAN, AN minus 1, FAN. So this we assume. So we are maintaining a min heap and we repeat the same process until a single element exists. So we maintain a forest. So we make forest. So this min heap we can so elements I will describe. This is min heap where the nodes are forests. And we use frequency. Frequency of forests for sorting. And not forest, this subtree. So forest is a collection of subtrees. The elements in the min heap are subtrees and we use frequency of the subtrees. And how to define a frequency of subtree? So frequency of a subtree we defined as, it is simply the sum over all A, call the subtree S. So simply take all nodes in the subtree and add their frequency. So this is defined as frequency of the subtree S. So this way we maintain a subtree. So initially we have this min heap A1 up to. So in the min heap the subtrees are isolated nodes A1 A2 up to an minus 1, an, and where these are sorted by their frequencies, fa1, fa2, and so on, fan minus 1, and here fan. So this is our initial min heap. It is a collection of subtrees, and they are sorted using the parameter frequency, and frequency of a subtree is simply the sum of the frequencies of the nodes in the subtree. So the algorithm is very simple. We simply extract two minimum elements, merge the subtrees, and insert back in the min heap. So in the iterative algorithm, we can write a loop like this. If this, so call this min heap m, just write this as m. So if m has at least two elements, then what we do is extract two minimum elements. Extract two minimum elements from m. So for simplicity, we can assume that the two extracted elements are, let them be ai, name them. We can take some label like xy. You can take, call them x and y. These are x and y, and with the corresponding frequencies fx and fy, and merge. So initially, according to our convention that these are sorted, so initially x will be this an minus 1 and this y will be an, having frequencies, just to give an example, an minus 1 and an. So what we do is next is merge the two subtrees. Merge the two subtrees, x and y. How we merge? So example I have already shown. Merge them like this. Call this subtree xy. This is the subtree xy with the corresponding frequency fxy is equal to fx plus fy. So we extract two minimum elements, merge them, update their frequency as, we call this new subtree xy, and update their frequency as the sum of the two frequencies. And after this we insert it back. Then insert this xy node into the min heap m. So the same process is repeated again and again until we get a single subtree in the forest. At that point we stop and we get the corresponding encoding. So when we stop, we output the encoding corresponding to the only subtree remaining, only subtree, or better we call final subtree, final subtree. So I have already shown the example how to maintain min heap of the forest and extract two minimum elements, merge them and insert it back into the min heap with updated frequency, which is the sum of the two subtrees, frequencies of the two subtrees. So now we have to prove that this is the optimal. We get an encoding with minimum possible average bit length. So we'll prove by induction. Prove by induction. So our induction statement is Pn the tree T returned by the algorithm with n inputs, a1 up to an with the corresponding frequencies fa1 up to fan gives the minimum possible average bit length. This is our induction statement. So first basis we start with two nodes because a single node is trivial. Single node means we have a single alphabet and we can use any encoding, like encode all with 0 or 1. This is unary encoding and it is trivial, nothing needs to be proven. So basis we start with n equal to 2 so that we can get binary encoding. So basis is very simple. We use this binary tree. Suppose the alphabets are A and B with frequencies FA and FB, corresponding frequencies. So A gets the code 0, B gets the code 1. Now what is average bit length? All this encoding gamma FA multiplied by length of 0 plus FB multiplied by length of 1, FA plus FB, and we know that FA plus FB is 1. So average bit length we get is 1. And less than this is not possible because if we make any further changes, we have to increase the length of code of either A or B. For the basis case, we can have the other possibilities, something like this. Either A or B, they will be at the larger depth. For example, this. So A will have code 0, B will have 1 0. So now if we compare the average bit length, it will increase. For example, here FA size of 0 plus FB size of 1 0. So this will change to 1 0. And if we compute, we get this as the new expression will become FA plus 2FB is equal to FA plus FB. This is already 1 plus FB. This is equal to 1 plus FB. So we are getting higher bit length, average bit length as before. So the best possible that we can do for the basis case is this. A is having encoding 0, B is having encoding 1. Next our induction hypothesis, we assume Pn minus 1. So our Huffman's algorithm gives optimal prefix codes for codes of length up to n minus 1. This is our assumption, and now we consider Pn. So here, suppose our algorithm on n inputs, original input gives tree T. So for n length a1 up to an, suppose output we get a tree T. So just consider after first level of iteration. So first level of iteration, under our assumption that this simplifying assumption fa1 up to fan, we get another tree, call it T prime, using, so this will reduce to of instance size n minus 1. Next level we get T prime. So here in T prime we merge an minus 1 and an, call it a single alphabet, name it an minus 1 an, having frequency fan minus 1 plus fan. Take it as a single node, apply this algorithm on the remaining inputs n minus of size n minus 1, get the tree T prime. So our assumption is, by our induction hypothesis, this has minimum possible average bit length. Now we compare. So before proceeding for the proof, we compare between average bit length using T and average bit length using T prime. What is the relation between the two? So the relation is very simple if we compare, and we'll prove this, and this proof will the result will enable us to prove our induction hypothesis. So first, before proceeding for the proof, we need a result between average bit length using T and average bit length using T prime. So assume that, again for simplicity, assume that when we combine a1 and a2, an minus 1 and just for simplicity write this an minus 1 an is combined to get w, with frequency fw is fan minus 1 plus f of an. So just for simplicity I am writing the combined word, combined alphabet an minus 1 an as w, and its frequency is fw is f an minus 1 plus fan. So now we'll prove a very simple relation between the two. Average bit length of T prime, how it compares with average bit length of T. So just subtract by fw. So average bit length of T prime is, start with average bit length of T and subtract fw, and proof is very simple. Just so in structure T and T prime are identical. The only difference is how we interpret the nodes. So if we make the structure of both T and T prime, we get identical, like some, just giving an example. So T prime, what will happen? It is something like this. Here T also exactly same structure, but how we interpret is different. So for example, in T prime we have a single node. We have a single node W with frequency fw. So here what happens, the structure is same, but here what happens, this w expands. So exactly same structure, instead of w we expand a single node like this, an minus 1 and an. This is the only difference, rest is identical. So now we can write the expressions for both abstract average bit length of t as well as t prime and compare the two using this equation. So first we write the expression of average bit length of t. Average bit length of t is sum over all x is in s. So s here is the alphabet, fx multiplied by depth in tree t of the node x. So this is the expression. So again we divide this in two parts. So if we compare the two, everything is identical except for these two nodes. So we simply separate out these two nodes and write the expression. So we write, separate out an minus 1 and an. So f an minus 1 multiplied by depth of the corresponding node in t an minus 1 plus the other node is an depth of node an in tree t plus remaining expression which is identical for both trees, sum of all x is not equal to either of these an minus 1 and an fx times depth in t of node x. Now the same thing we convert back into expression for t prime. So for t prime, this term is identical, only difference we get in these first two terms. So we write this as, so first two terms how we write. So once again just compare depth of w with depth of an minus 1 and an. So we get a simple observation that depth of an minus 1 as well as an, they are one more than depth of w. So we apply this observation and write this as, and also so their depth is depth of w plus 1. So very simple observation we make and simplify our expression as we are converting to the expression of t prime, average bit length. So write this as fan minus 1 plus fan, both having depth 1 plus depth in tree t prime of w plus the remaining expression. So remaining expression we can easily convert in t prime, both are identical. X is not equal to an minus 1 an fx times depth in t prime of x. So now just see what is this expression. This, it is fw. So just replace it with fw. So we get this is equal to fw 1 plus depth in t prime of w plus the remaining expression. x is not equal to an minus 1 and an fx times depth in t prime of x. Now we can simplify this. Fw plus, separate out, Fw times depth in t prime of w plus the remaining expression sum of all x is not equal to an minus 1 and an fx times depth in t prime of x. Now just see, we are combining these two. So just observe that our tree t prime, it does not have these elements. X is not equal to these and x is in S. So but it has the node W. So just combine the two and get the complete expression of, here x is in S, complete expression for abstract bit length of t prime. Just correcting the expressions, x is in S. So we get our result Fw plus average bit length of t prime. So this is the relation between the two, that how to get average bit length of t prime, just subtract by Fw from average bit length of t. This is our relation and this will be used in the proof. So next we proceed for the proof. So once again, just remember, for the original instance a1 up to an of size n, our output is tree t, and the next step we have some instance of size n minus 1 and our tree is t prime, and by our induction hypothesis average bit length of t prime is minimum possible. This is our hypothesis. Now we want to prove that. So this is our induction hypothesis Pn minus 1, that average bit length of t prime is minimum possible. So for proving Pn, we have to prove that, average bit length of t is minimum possible. This we have to prove. So this is a very simple proof using contradiction. If t is minimum possible, then there is nothing to prove. Otherwise, we proceed like this. So suppose if t is not optimal, then assume that z is optimal. Assume that z is optimal and it has so just remember the property of optimal subtree. So just remember the property of optimal subtree, that if we consider the largest leaf nodes having, the two sibling leaf nodes having largest possible depth, they should be of minimum frequency. So just compare this z with our t. So our so just compare the two. According to our algorithm, the two lowest frequency nodes are an-1 and an with frequencies fan-1 and fan. So we merge these two according to our algorithm. And if we consider Z, assuming that it is optimal, so just apply the previous property of optimal prefix code, that the same thing applies, means the two minimum frequency nodes, and they are an-1 and an, they are at the largest possible depth. So same thing happens here also, this an-1 and an, they are at the largest possible depth. Because the lowest possible frequency, two lowest possible frequency, they are assigned to the two largest possible nodes, two nodes with the largest possible depth. So, and they are an-1 and an. So they are at the largest possible depth. So in Z we have something like at the largest possible depth an-1 and an. So here our assumption is that average bit length of Z is less than average bit length of T. So now what we do is, from T we make T prime and compare the average bit length, and from Z we make Z prime and make average bit length. So from going from Z to Z prime, we get these expressions. Average bit length of Z prime is average bit length of Z minus FW. We are simply merging the two, and same thing happens for T prime also. Average bit length of T prime is average bit length of T minus FW. So now we compare the two and we get a contradiction. So starting from this average bit length of Z is less than average bit length of T, just subtract FW from both sides, implies average bit length of Z minus FW is less than average bit length of T minus FW. Now convert this into average bit length of Z prime is less than average bit length of T prime. But here we are getting a contradiction. Why? Because our assumption is that this is having the minimum possible average bit length. So we cannot have any Z prime having less average bit length. So we are getting a contradiction. So it means that our initial assumption is wrong. Initial assumption that T is not optimal, this is wrong. So T has to be optimal. So this completes the proof that the iterative algorithm, Huffman's algorithm that we have designed, gives the minimum possible average bit length. So this Huffman's algorithm, it has time complexity n log n, and we can easily derive the time complexity. So this is the algorithm. So here we have to maintain a min heap, and here we start with this assumption, and initializing a min heap, we can do this in n log n time, or if we sort it again, it will take big O of n log n for initializing the heap. Now the operations done are, so this initialization step, it takes big O of n log n. Now what min heap operations we are doing is extracting. So we are extracting two minimum elements. So extraction can be done in big O of log n time, two extractions, total big O of log n time. And then we are, so merge operation. So merge operation is very simple. It takes only constant time, and after merging we insert in the min heap. So this operation also takes big O of log n time. So net complexity is big O of log n, and we are doing this for at most n times. So the net complexity we get is n multiplied by big O of log n. This is equal to big O of n log n. This much plus the earlier big O of log n, n log n, big O of n log n. Net we get is big O of n log n. So this is the time complexity of Huffman's algorithm. It is very efficient, only big O of n log n. And here also we can see the three characteristics of greedy algorithm. So the first is we are incrementally building the solution even before solving the sub problem. So here we are incrementally building our solution. So the tree that we are incrementally building, these are the partial solutions, and the sub problems we get is a single sub problem, and the single sub problem is represented in the min heap. So we are maintaining a min heap, and it represents a single sub problem. So, and one more condition, the greedy choice property. So the greedy choice property is we are choosing the two minimum elements. This is the greedy choice property. We are making local decision. This is local optimum. Local optimum implies global optimal. Global opt. This is the greedy choice property.